All right, welcome to another deep dive. You know the drill by now, right? You send us stuff,
Stuff you're curious about?
we go through it, and then we bring you, well, like the good stuff, you know?
The nuggets.
The nuggets of knowledge that you really walk away with.
The stuff that sticks.
The aha moments.
So you can be, the most informed person in the room on a given topic.
Yeah, and we want to do that fast.
Quick and dirty.
Without, overwhelming you with a bunch of jargon.
Yeah, we'll try and keep it clear.
Yeah, keep it fun. So today's topic,
Very cool one.
it is a really cool one.
It is.
AI, artificial intelligence, specifically.
Adversarial search in games.
Ooh, yeah.
Based on, what you sent us.
Based on what you sent us, this is not just about games on your phone, though.
No. When we say games, we're thinking a little more broadly.
Yeah, think about AI, and AI having to kind of go up against
Another intelligent entity.
another intelligent entity.
Yeah.
They both have their own goals, right?
Yeah, their own goals.
Mhm,
And those
yeah.
goals are often directly in conflict with one another.
Yeah, so it's not just like, solving a problem in the environment. It's
Yeah.
like you're trying to outmaneuver
An opponent.
an opponent who's trying to do the same to you.
Exactly. It's a battle of wits.
It is a battle of wits. And this isn't just about understanding board games, though.
Yeah.
This is kind of like a shortcut to understanding decision-making.
Strategic decision-making.
Strategic decision-making in all kinds of competitive situations.
Yeah,
Business.
you name it.
Politics.
You name it, wherever you have that strategic interplay.
So the range of what we're going to talk about is pretty big,
Extensive.
extensive. We're going to talk about those deterministic games.
Perfect information.
Perfect information games like chess and Go. So, both players.
See the entire state of the game.
Yeah, they can see the whole board. They know what the score is, whatever.
No hidden information.
Then there's games with chance.
A little bit of randomness thrown in.
Backgammon.
Backgammon, yeah.
Dice.
Dice rolls.
Okay, now that's interesting. But then we're going to get even more complicated.
Uh-oh.
We're going to talk about games of imperfect information
Oh, yeah.
where you don't actually know.
Everything that your opponent knows.
Yeah, like poker.
Poker.
You don't know what cards they're holding.
Or Kriegspiel.
Kriegspiel, this crazy, crazy version of chess.
It's chess.
You can't see the other person's pieces.
You only get told certain things by the referee.
Oh, it's so cool. We're going to explore how AI tackles all of this.
All the different flavors.
All the different flavors.
That's adversity.
Of adversity. We're going to uncover some really surprising things about how AI approaches this.
And try and make sense of the technical details.
Without getting too bogged down. All right, so where do we begin? When AI is trying to face these opponents, what is the basic approach? Where do we even start with this?
Well, the first thing to grasp is the idea of game theory in AI. So it's not just about planning in the face of uncertainty, like we might do with weather forecasting.
Right.
It's about explicitly modeling those adversaries,
Okay.
recognizing that they have their own objectives, their own goals,
And those goals are probably in conflict with your goals.
often directly in conflict.
Okay.
Now, to make things a little easier to start, we often focus on a specific type of game,
Okay.
deterministic, two-player, turn-taking games,
All right.
with perfect information and a zero-sum outcome.
Ooh, a lot of terms
They're all
though.
jargon. But these are your classic board games. Chess and Go fit this bill perfectly.
Chess and Go. All right. So two-player, obviously.
Two-player, you take turns.
Back and forth. Okay.
Perfect information means at every point in the game, both players see the whole board.
Okay.
So no hidden information.
So no hidden information, no simultaneous moves.
No simultaneous moves.
Okay, got it.
And zero-sum means that any gain for one player is a direct loss for the other.
Okay, so there's no way for them to both kind of win together.
No.
Got it. All right, so within these types of games, what are like the basic elements that the AI is working with?
Well, we talk about moves, which are the actions a player can take,
Okay.
and positions, which represent the state of the game.
Okay, that makes sense.
Then we have our two players, conventionally named Max and MIN.
Max and MI. All right, classic.
Yeah, Max is usually the player we want to win.
That's the good guy, the hero,
And MIN is the
the
opponent.
bad guy. Okay, I'm following so far.
So a game is then formally defined by a few key components.
Okay, hit me.
We have the initial state,
Okay, the starting point.
whose turn it is to move.
All right.
The set of legal moves.
So all the possible actions you can take from a given position.
Exactly. The transition model, which describes how a move changes the game state.
Okay.
A condition for when the game ends, which we call the terminal test.
So that's like checkmate in chess, or?
Checkmate in chess, exactly, or a draw. And finally, the utility or payoff for each player at those terminal states.
Okay, so for chess, the initial state would be the starting board setup.
Exactly.
Legal moves, all the different ways you can move your pieces.
Correct.
The game ends with checkmate, stalemate, or a draw.
Right.
And the utility for max, let's say, could be +1 for a win,
+1 for a win,
-1 for a loss,
and add a 1 for a loss.
and 0 for a draw.
0 for a draw. Perfect.
It makes perfect sense. Okay, so now we have this idea of all these potential sequences of moves and game states. Can we visualize this somehow?
We can. We use what's called a game tree.
A game tree, okay.
It basically branches out from the initial state,
Okay.
showing every possible path the game can take.
Like a massive flow chart of the entire game.
Exactly.
Oh my gosh, I can imagine that would get very big very quickly.
It does.
Like exponentially bigger.
Exponentially, yeah. Even for a simple game like tic-tac-toe.
Yeah.
The complete game tree is big.
Big.
Manageable, but big.
Okay.
Now, chess.
Forget about it.
Oh, chess. We're talking an estimated 10 to the power of 40 possible nodes.
That's mind-bogglingly huge.
Mind-boggling. So the game tree becomes this theoretical concept,
Okay.
something far too large to actually map out.
All right, so now Max wants to win. Of course, Max wants to win.
Of course.
How do we figure out the best way to make that happen within this insane tree of possibilities?
Max's objective is to discover a winning strategy.
Okay.
Now, this isn't just a single move.
Right.
It's a plan.
Okay.
A conditional plan that dictates what to do in every possible situation.
Okay, for every possible move that MIN might make.
Every possible move that MIN might make. Now, for games where it's just win or lose,
Okay.
it's like solving a planning problem
Right.
with uncertainty about the opponent's actions.
Uncertainty, yeah, because you don't know what they're going to do.
You don't know what they're going to do. But for games where there are different scores possible,
Okay.
we use what's called minimax search.
Minimax. So it sounds like we're maximizing something A and D minimizing something.
You got it. For every state in the game tree,
Okay.
we can calculate its minimax value.
Okay.
Now, this represents the best possible outcome for max,
Right.
assuming, and this is key, that both players play optimally
Okay.
from that point forward.
From that point forward. Okay.
So for a terminal state, the minimax value is just its utility.
Okay.
The final score, +1, mamma 1, 0, whatever it is.
Makes sense.
But for a non-terminal state, things get interesting.
Okay. I'm intrigued. Tell me more.
If it's MX's turn,
Okay.
they're going to choose the move that leads to the state with the highest minimax value.
Okay, so they're maximizing the chances of winning.
They're maximized. But if it's MIN's turn,
They're going to try to minimize Max's outcome.
they're going to choose the move that leads to the lowest minimax value from Max's perspective.
Okay, so it's like working backward from the end of the game.
Exactly.
Figuring out the best move at each step along the way.
You're getting it. Think about that simple two-ply game tree.
The one we've all seen in textbooks.
Yeah, the classic one.
Okay.
The bottom level shows the final utilities for Max.
Okay.
The MIN nodes right above them.
Okay.
They're going to choose the minimum of the utilities of their successor states.
Okay.
And then the Max node at the top
Okay.
chooses the maximum of the values coming from the MIN nodes.
Got it. So it's this back and forth, right?
Back and forth.
Maximizing,
You know,
minimizing.
This backing up of values, as we call it,
Okay.
determines the minimax value of the initial state.
Okay.
And that tells us the optimal first move for Max.
That's the minimax decision.
A minimax decision.
This is all based on the idea that your opponent is playing perfectly right. What if they're not?
Ah, great question.
Because, in the real world, people make mistakes.
All the time.
Yeah, all the time.
If MIN plays suboptimally,
Okay.
Max is going to do at least as well,
Okay.
and potentially even better, than against a perfect opponent.
Right.
But here's the thing. It's not always best for Max to stick to that minimax optimal move
Yeah.
if they know their opponent is prone to errors.
Oh, interesting. Because there might be a more risky move.
Riskier, yes.
Or that could lead to a bigger win.
Bigger win, absolutely,
If the opponent messes up.
if the opponent blunders.
Okay, so there's this kind of balance between
Balance, yeah.
playing it safe, like for the theoretical best outcome,
The theoretically best outcome, yep.
and trying to exploit weaknesses.
Exploit those weaknesses.
Okay, I like it. So this whole thing, this calculation, this is what the minimax search algorithm does.
It is.
It figures out the best move to make.
It's a recursive, depth-first exploration of that whole game tree.
Depth first, meaning it goes all the way down one path before checking out other options.
Exactly. It goes deep.
Okay, and this leads us to the problem of complexity.
It does.
Right.
If the maximum depth of the game tree is M, and there are B legal moves at each step.
Okay, that's the branching factor.
That's the branching factor. The time it takes to run the minimax algorithm
Okay.
is on the order of B raised to the power of M.
Oh, boy.
Exponential growth.
That's a big problem. That's a huge problem, right?
Yeah, it's a huge problem.
Especially for a game like chess, with a high branching factor A and D, a long average game length.
Exactly. You're searching an astronomical number of states.
So pure minimax just doesn't really work in practice.
It's impractical for complex games,
Okay.
but it's important.
Why is it important?
It gives us the theoretical foundation for analyzing games,
Okay.
and it serves as the basis for more practical algorithms.
Okay, so it's like the starting point.
The starting point, yeah. A theoretical ideal to aim for.
Now, what happens when you have more than 2 players?
Oh, multiplayer games. They get even more interesting.
Okay, yeah, because now you've got all these different alliances and things that could potentially happen.
Alliances, betrayals.
Does minimax still work?
It does, but it's more complex. Instead of a single value for a state,
Okay.
we now have a vector of values.
A vector.
One for each player.
Okay, so like if you have 3 players,
3 players, yeah.
you have 3 values for each state.
One for player A, one for player B, and one for player C.
Okay.
And when you back up those values,
Okay.
each player chooses the move that leads to the best outcome for themselves.
Okay, so even in a multiplayer game, everyone's still looking out for number 1.
Absolutely. They're all selfish.
There's AI. Okay. But this selfish behavior, it can actually lead to alliances forming.
It can. It's fascinating.
How does that work?
Imagine 2 players who are both weaker than a third player.
Okay.
It might be in their best interest to team up.
To gang up on the strong guy.
Just gang up, exactly.
The enemy of my enemy is my friend.
Exactly. And these alliances, they can be fluid.
Okay, so they can change as the game goes on.
They change as the balance of power shifts.
Oh, that's cool. So even with these simple rules, you can get some really complex behavior emerging.
Very complex.
Now, we talked about the huge size of the game tree.
Yeah, that's a problem.
We're going to have to deal with that somehow.
Yeah.
You mentioned pruning earlier. What does that mean?
Pruning. So the game tree is huge.
Huge.
We need ways to reduce the search space.
Make it smaller.
Make it smaller. And the main method we use is called alpha-beta pruning.
Alpha-beta pruning. Okay, what is that?
It's a way to eliminate parts of the tree that don't affect the final decision
Okay.
without actually having to look at them.
Okay, that sounds like magic. How does that work?
Think about that 2-ply game tree again.
Okay.
As we're calculating those minimax values.
Yeah.
We keep track of 2 values.
Okay.
Alpha,
Alpha.
which is the best value that Max has found so far.
So it's like the minimum score that Max is guaranteed to get.
Yeah, you can think of it that way.
Okay.
And then we have beta,
Beta.
which is the best value that MIN has found so far.
Okay, so that's like the maximum score that MIN is willing to let Max get.
That's a good way to put it.
Yeah.
Now, imagine we're looking at some moves for MIN.
Okay.
If we find a move that would give a value less than or equal to alpha,
Okay.
Max would never choose to go down that path.
Right, because they already have a better option.
They already have a better option, so we can just prune that whole part of the tree.
We can just chop it off.
Chop it off. We don't even have to look at it.
Okay, that's efficient.
Very efficient. Same thing if we're looking at moves for Max.
Yep. Mm-hmm.
If we find a move that leads to a value greater than or equal to beta,
MIN would say, nope, not going to let that happen.
not going to let that happen.
Right, so prune again.
Prune again.
Yeah.
So by updating these alpha and beta values,
Okay.
we can drastically reduce the number of nodes we have to examine.
That's pretty clever.
A very clever algorithm.
Yeah.
Now, the order we look at the moves matters a lot.
It does. How so?
If we happen to look at the best moves early on, we can tighten those alpha and beta bounds quickly.
Right, so you get more pruning.
More pruning.
Yeah.
In the best case scenario,
Okay.
with perfect move ordering,
Wow.
alpha-beta pruning can reduce the number of nodes we examine drastically.
Drastically. Okay, so in the best case, how much better does it get?
Instead of b to the power of m,
Okay.
it becomes b to the power of m divided by 2.
Wow. So it's like having the exponent.
Exactly. Having the skull.
So for chess, that could be like reducing the branching factor from, what, 35?
35 or so, yeah.
Down to like 6?
Down to 6, yeah. Huge improvement.
That's a huge GE improvement.
Now, perfect ordering isn't realistic.
Right, because you don't know the best moves ahead of time.
You don't know. But even simple heuristics can get us close.
Okay, like what? Give me an example.
Like try and capture moves first.
In chess.
In chess, yeah. And then there are more dynamic techniques,
Okay.
like the killer move heuristic.
Killer move. Sounds intense.
Sounds intense. We prioritize moves that have worked well in the past.
Okay, so it's learning from experience.
Learning from experience, yeah. Or we use iterative deepening
Iterative deepening.
to refine the move order.
Okay.
And then there are transposition tables.
Transposition tables.
They act like a cache.
Okay.
They store the results of previously explored states.
So if the AI encounters the same position again, it doesn't have to recalculate everything.
Exactly. Saves a lot of time.
It's like a short-term memory for game positions.
Exactly.
That's really cool. So it's all about making smart choices about what to look at and remembering past results
Smart choices and good memory.
to make the pruning as effective as possible.
Efficient pruning.
Now, your sources also mention these different strategies like type A and type B.
Ah, yes. Shannon's type A and type B.
From the early days of computer chess, can you explain those a bit?
So type A, it involved a broad but shallow search,
Okay.
combined with an evaluation function.
So you look at lots of possibilities, but not very deeply.
Not very deeply, yeah.
Okay.
And then you use this evaluation function to estimate the value of the positions.
Okay.
Type B.
Type B.
It focused on a deep but narrow search.
Okay, so you go really deep, but only down certain paths.
Only down promising paths, yeah. Historically, chess programs tended to favor type A,
Okay.
while Go programs often use type B.
Okay, because Go has such a huge branching factor.
A huge branching factor, yeah. Interestingly, more recent advances, even in chess,
Okay.
have seen a resurgence of deeper, narrower search methods.
Okay, so it's kind of like both approaches have their strengths and weaknesses.
Strengths and weaknesses, yeah. And the best approach might depend on the game.
All right, so even with all this pruning, we still can't search the entire tree for really complex games, right?
Right.
Within a reasonable amount of time. That's where heuristics come in.
Exactly.
Can you tell me more about those?
So in practice, we have to cut off the search somewhere. Instead of going all the way to the end of the game,
Right.
we use a heuristic evaluation function,
Okay.
often called eval,
EVLL.
to estimate how good a non-terminal state is.
Okay, so it's like making an educated guess about how likely you are to win from a certain position
Exactly.
based on the current state of the game.
The current state, yeah. We also need a cutoff test.
A cutoff test. Okay, what's that?
It tells us when to stop searching.
Okay.
It could be based on the depth we've reached
Okay.
or some specific properties of the game state.
Okay, so like if you've looked ahead 5 moves, just stop there and use the evaluation function.
Exactly.
Okay, so what makes a good evaluation function?
Well, first, it needs to be fast.
Fast. Okay.
Because if it's slow, it defeats the whole purpose of cutting off the search early.
Right, you might as well just search the whole tree if it's going to take that long.
Exactly.
Yeah.
And crucially, it needs to correlate with the actual chances of winning.
Okay, so it needs to be accurate.
Accurate, yeah.
So how do you even design something like that for a game like chess, which is so complex?
Most evaluation functions analyze features of the game state.
Okay.
For chess, this could be things like
Okay.
the number and type of pieces,
Okay, yeah. Material advantage.
control of important squares,
Makes sense.
the pawn structure,
Okay.
king safety.
Yeah. You don't want your king hanging out in the open.
No, you don't. Each of these features gets a weight.
Okay.
That reflects its importance.
So having an extra queen would be a really big positive weight.
Yeah, big positive weight. Historically, these weights came from human experts.
Okay, so like grandmasters would say, a pawn is worth this much, a knight is worth this much.
Yeah, exactly. And then you'd add up these values to get a score for the position.
Okay, so a simple weighted sum.
A weighted linear function.
But this kind of assumes that the features are independent, right?
It does.
Which isn't always true.
Not always true.
Like having 2 rooks on an open file might be way more powerful than just the sum of their individual values.
Exactly. So modern programs use more complex combinations,
Okay.
nonlinear functions,
Okay, more sophisticated.
to account for those interactions.
Okay.
And increasingly, we're using machine learning
Machine learning, oh yeah.
to learn those features and weights automatically
From tons of data.
from tons of data.
Okay, so the AI is figuring out for itself what makes a good position. That's pretty cool.
Very cool.
Now, how does alpha-beta search use this evaluation function?
We modify the algorithm a bit
Okay.
when we hit the cutoff point.
Okay.
Either we've reached the maximum depth
Okay.
or the position is stable enough to evaluate.
Okay.
We call the eval function
Okay.
and return that estimated score.
Okay.
We use techniques like iterative deepening
Yeah, we talked about that.
to gradually increase the depth
Okay.
and get better move ordering.
Right.
And there's quiescent search
Quiescent search.
to avoid evaluating unstable positions.
Okay, like positions where a capture is about to happen.
Exactly. You don't want to evaluate a position right before your queen gets taken.
Right, that would give you a misleading score.
Very misleading. So quiescent search extends the search in those cases.
Okay, just to make sure you're evaluating a stable position.
A stable position. Now, there's also the horizon effect,
The horizon effect, okay.
where a delaying tactic might push a bad outcome beyond the search horizon.
Okay, so it makes a bad move look good.
It looks deceptively good.
Because the bad stuff hasn't happened yet within the search depth.
Exactly. We can use singular extensions to help with that.
Singular extension.
They extend the search for clearly superior moves.
Okay, just to make sure you're not missing something important.
Right. Then there's forward pruning,
Forward pruning.
like beam search and PROBCUT.
Okay.
They aggressively prune unpromising moves
Okay.
to save computation.
But there's a risk, right?
There's a risk, yeah.
You might miss the best move.
You might miss the optimal move.
Okay.
And there's late move reduction.
Late move reductions.
They reduce the search depth for moves that are less likely to be good.
Okay, so it's like, this move probably isn't great, so I'm not going to waste a lot of time thinking about it.
Exactly.
So it's this constant balancing act between searching deep enough
Deep enough.
and evaluating accurately,
Accurately.
all within a limited time.
Limited time.
Now, sometimes, instead of searching,
Sometimes searching is just not the best way.
you can just look up the answer.
Exactly.
Is that what you're saying?
That's what I'm saying.
Okay, tell me more.
So for the very beginning of the game,
The opening.
the opening,
Okay.
and the very end,
The end game.
the end game, strong programs often rely on lookup tables
Lookup tables. Okay.
instead of searching.
Okay, so for openings,
Openings, yeah.
these tables are based on human knowledge
Human knowledge, yeah.
and databases of played games.
Massive databases.
So it's like the computer has memorized the best opening moves.
Exactly.
Okay, that makes sense.